Okay, so now we're done with maximization problems and now we proceed to minimization problems. There are some differences in solving maximization problems and minimization problems. In the graphical method, the only difference would be how you find for the optimal solution, because in finding the optimal solution in the graphical method, you are to plot the objective function, and for maximization problems, you move that objective line away from the point of origin, and then for minimization problems, you move it nearer or towards the point of origin, and then in both cases, the last point that they touch or that the objective function will touch is the optimal solution. Although the difference is the direction they're going to. For maximization, it's farther away from the point of origin. For minimization problem, it's towards the objective function. Okay, but for simplex method, there is a huge difference. Okay, but we go to that later. Okay, now let's just solve this problem first using the graphical method. Like I said, there's not much of a difference. Okay, so let us just proceed to solving this problem. Okay, and I will be showing it to you, but not much talking, just solving, because we have already, or I have already guided you step by step in the previous video, in the maximization video. So let's just solve this. Okay. Okay, so we are trying to minimize the cost, which we will be representing using the variable C. Okay. So, we minimize the cost. But what is the cost? Okay, cost would be, well, chicken's best cost 7 per ounce. So that would be 7B plus 5 per ounce for chicken meal. Okay, subject to these restrictions, to these constraints. Okay. Okay, so this is our linear programming mathematical model. We have here the objective function and the constraints. Okay, so now we are ready to plot these constraints into the objective function, into the Cartesian plane. Okay, so similar to what we have done in the maximization problem, we just set these variables to 0 so that we could get the intercepts. Okay, and then when we have the 2 points, we can now plot them. Okay. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's 10. 0, 10. 1, 2, 3, 4, 5. This would be 5. Okay, 5, 0. Oops. So this is a greater than or equal to inequality. Therefore, the region we shall be shading would be to the right or above. Actually, this entire region here. Okay, but it would take us the whole day to put color to this. So okay. Actually, it also extends here and down. Okay. Second constraint, if m is 0, b is equal to 4. If b is 0, m is equal to 8. Therefore, we have 4, 0, and 0, 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay. So this line here is parallel to our first objective line. And therefore, this is a redundant constraint. Okay, we don't need this constraint. Okay, with or without this constraint, the feasible region is not going to change. Okay, but okay, let's just plot it anyway. Okay, this second constraint will cover slightly a greater region because of this region here. But what we are looking for in a feasible region is the set of points that would satisfy all of the constraints. Okay, so this region here, this small region in between these lines, they only satisfy the second constraint, but not the first. So this could be eliminated. This is a redundant constraint. Okay, so automatically, if you see parallel lines, or if you see a constraint line parallel to another constraint, then one of them is redundant. Okay, so let's now proceed to the last constraint. 16b plus 18m is equal to 180. If b is 0, then m would be 10. And therefore, we have 0, 10. 180 divided by 16 is 11.25. So, b would be 11.25 if m is 0. So, we have the point 11.25, 0. Okay. So, where is 0, 10? M is 10. Yeah, 0, 10. Okay. So, here. Okay, and 11.25. So, 5, 6, 7, 8, 9, 10, 11.25. So, here. Okay. Okay, but this is a less than or equal to inequality, and therefore we are to shade this portion. Okay, so, and of course, the entire first quadrant. Okay, so we have the feasible region here. This is the feasible region. Okay, because these are the set of points that satisfy all the constraints. Okay, this is our feasible region, and it is bounded by the points, this one 0, 10, 5, 0, and this is actually 11.25 and 0. Okay. So let us now test. Well, actually in the graphical method, you are to plot the objective line and then move it nearer to the point of origin. Okay, and then the last point that it touches would be the optimal solution. But we don't have to do that. Okay, let's just substitute these corner points into the objective function. Okay. So the objective function is 7b. Okay, 7b plus 5m. And we have 3 corner points. The first one is 0, 10. The second one is 5, 0. And 11.25, 0. Okay? So this is in the format BM. Okay? So first one, 7 times 0 plus 5 times 10, that would be 50. Okay? And then 7 times 5 plus 5 times 0, that would be 35. And lastly, 7 times 11.25, okay, times 7, that's 78, 75 plus 0. Okay? 78, 75. And among these three, this is the lowest, this is the minimum. It's the lowest cost. And therefore, our optimal solution is 5, 0. We are to buy 5 chickens best. Okay? And we don't have to buy a chicken meal. Okay? This is our optimal solution. By the way, the cost would be 35 pesos. Okay? This is our optimal solution. And after that, we now proceed to... So now we try to solve this same problem using the simplex method. In this method, we are actually going to use solving the same problem using the simplex method. Let's just put this aside and then we will compare. At the end of our solution using the simplex method, we are going back to this and see if we have arrived at the same answer. 12b plus 6m is greater than or equal to 60. 2b plus m greater than or equal to 8. 16b plus 18m is less than or equal to 180. And of course, our non-negativity constraints. Okay? So, we are going to check first, okay, in solving a problem, a minimization problem through the simplex method. First thing we have to do is to check whether all inequalities, well, actually, in the simplex method, we're going to ignore the non-negativity constraints. We're not going to need them. Okay? And then, next would be to check the remaining constraints if they are expressed as greater than or equal to. Okay? Because in the simplex method, the sign, okay, of the numbers is very important. Okay? Whether it is positive or it is negative, it's actually a big deal. Okay? That is why we have to convert this into a greater than or equal to. Okay. Now, how are we going to convert this into a greater than or equal to inequality? Okay. So, there is this law in inequalities wherein if you're going to multiply a negative number to both sides, okay, it will reverse the sign. Okay. If you're going to multiply a positive number, the sign is not going to change. Okay? But if you're going to multiply a negative number to either side, okay, or I mean to both sides of the inequality, the sign will reverse. So we multiply negative 1 to each side of this inequality. So that would give us negative 16b minus 18m. Okay? And then the sign will reverse. It now becomes greater than or equal to, and then negative 180. Okay, so now all of the constraints are expressed as greater than or equal to, and now we are ready to proceed to the next step. Now, the idea here is to convert this minimization problem into a maximization problem. The idea here in transposition is that we are going to write the coefficients of these functions into a matrix and then we transpose. Okay? The rows are going to be columns. Okay? So there will be a change in the position, okay, of these coefficients. So now we write them down. Okay? We first write the coefficients of our constraints and then lastly our objective function. So 12, 6, 60. Okay, by the way, we are going to draw broken lines, okay, to separate both sides of the inequality. And then 2, 1, okay, and then 8, 16, 18. By the way, we follow this new converted inequality. So negative 16, negative 18, and negative 180. And then lastly, our objective function. By the way, this is B, this is M. So we just follow. Okay, our B here is 7. Our M is 5. And then this letter C here will be represented by the number 1. Okay, so this is our... Okay, so as mentioned, we are going to transform the rows into columns. Okay, so this is the first row. It now becomes column number 1. Okay, so 12, 6, and then followed by 60, and then 2, 1, 8, negative 16, negative 18, negative 180, and then 7, 5, 1. So now we have completed the transposition process, and now we have a transposed matrix. Okay, so from our matrix, we are now going to derive our maximization problem. So as I mentioned a while ago, the idea here is to transform this minimization problem into a maximization problem. Okay, so now from this transposed matrix, we are now going to derive our maximization problem. Okay, so we begin with the third row because if you remember in our maximization video, these two here are the constraints. Okay, those that are above these dotted lines, these are the constraints, and then below the dotted lines, this is what you call the objective function. Okay, so maximize P. Okay, we're going to use P because this is a maximization problem. Okay, so actually guys, P here is this, okay, which is on a different side of, which is on the other side of the equation. Okay, and then 60x plus 8y minus 180z. Okay, so this is P. This one here is P. If you remember in the original matrix, this one here is C. Okay, so in the transpose matrix, this is now P. Okay, which is on a different side of the equation from these three. Okay, so we introduce x, y, and z because we cannot use b and m. Okay, we're going to use b and m later, but in a different capacity. We're going to use b and m as our slack variables. So now we proceed to our constraints. First would be 12x plus 2y minus 16z, okay, is less than or equal to 7, and then 6x plus y minus 18z is less than or equal to 5. Okay, we're going to reverse the sign. Okay, and then because this is already transposed, Okay, and then we're done. Okay, this is now our linear programming model. And the next thing we're going to do would now be to create our Simplex Tableau. Okay, this is what we call the Simplex. Okay, Tableau. Okay, so Simplex Tableau. Now, before we can create our Simplex Tableau, we first have to express this objective function in such a way wherein one side will be 0. So, these three terms here will just go to the other side. Okay, and when they go to the other side, their signs will reverse. So, negative 60x minus 8y plus 180z plus p is equal to 0. Okay, and then next our constraints. Okay, we have to convert our constraints into equations, and in doing so, we are to introduce slack variables, which will be b and m. Okay, as I have mentioned a while ago. So 12x plus 2y minus 16z plus the slack variable b, okay, is equal to 7. And then finally 6x plus y minus 18z plus m is equal to 5. And now we're ready to create our Simplex Tableau, beginning with the constraints first, and then this one will become last. Okay, so let's label x, y, z, the slack variables b and m, and then p. Okay, we begin with the constraints. Okay, so 12 to negative 16, 1, we have no m's here, we have no b's here, we have no p's here as well. Okay, and then 7, and the next 6, 1, negative 18, we have no b, we have an m, no p. Okay, and then 5. Then finally our objective function, negative 60, negative 8, 180, no b, no m, we have a p here, and then 0. So this is now our Simplex Tableau. And just like in maximization problem, we begin the simplex process by finding in the third row the most negative number. This is the number that is farthest to the left of the point of origin in the Cartesian plane, and this would be negative 60. Negative 60 here is our most negative. Okay, we only have two negative numbers, negative 60 and negative 8, and between these two, the more negative number is 60. Okay, so this is now what we call our pivot column. Okay, and the next thing we're going to do is to find for our pivot element, and to do that we have to make some comparisons. Okay, we divide this number by the number here, by the number that corresponds to it, okay, in the pivot column. Okay, so 7 over 12. Okay, let's just test them. 7 divided by 12 is 0.583. Okay, so this is 0.583. Okay, and then 5 over 6 is this is 0.833, and the smaller number would be 7 over 12, and that is why 12 here, okay, becomes now our pivot element. Okay, and now we can perform our row operations. Okay, we can now perform our row operations. Okay, so our first operation, again, reminding you of our goals here. Okay, the pivot element must be converted to 1, and then all other numbers in the pivot column must be converted to 0. Okay, through our row operations. Okay, so our row operations Okay. The first one would be to convert this pivot element into 1. And how are we going to do that? We multiply 1 over 12 to all the numbers in row 1. And that would be our new row 1. Okay? X, Y, Z, B, M, P. Okay? And now we are going to perform our first row operation. So 1 over 12 times 12 would be 1. 1 over 12 times 2 would be 1 over 6. Okay? And then negative 16 times 1 over 12 would be negative 4 over 3. Okay? And then 1 over 12 times 1 would be 1 over 12. Okay? 1 over 12 times 0 would be 0. And then 1 over 12 times P. Sorry, times 0 would be 0. And then 7 over 12. Okay? Next would be to determine what our next row operations would be. And the goal here again is to make these numbers be equal to 0. Okay? So, we will be having this row operation, negative 6 times the new row 1, and then we add it to row 2, and that becomes now our new row 2. So let's do that. Negative 6 times 1 would be negative 6 plus 6, 0. Negative 6 times 1 over 6, that would be negative 1. Okay, plus 1 would be 0. Okay, negative 6 times 4 over 3. So, we can cancel out negative 6 and negative 3. Okay, that would be 2 times 4. So, 8. Okay, negative 6 times negative 4 over 3 is 8. Okay, plus negative 18, that would be negative 10. Okay, and then next, negative 6 times 1 over 12, that would be negative 1 half. Okay, plus 0, that would be negative 1 half. Okay, negative 6 times 0 is 0, plus 1 would be 1. Negative 6 times 0 is 0, plus 0 would be 0. Okay, and now, next, negative 6 times 7 over 12. So that would be negative 7 halves, 7 over 2. Okay, negative 7 over 2 plus 5. Okay, 5 can be expressed as 10 over 2. Okay, so let's have a side computation. Or no need. Okay, so negative 7 over 2 plus 10 over 2, okay, would be 3 over 2. Okay, that's 3 over 2. Okay, again, negative 6, okay, times 7 over 12, that would give us negative 7 over 2 plus 5, okay, which we can rename as 10 over 2. So negative 7 over 2 plus 10 over 2, that would be 3 over 2. Okay, and finally, our last row operation, okay, to convert this negative 60 here into a 0, okay, would be 60 R1 plus R3 would be our new R3. Okay, so let's just perform this row operation. 60 times 1 is 60, plus negative 60 becomes 0. 60 times 1 over 6, that's 10. Okay, plus negative 8, that becomes 2. Okay, and then next, 60 times negative 4 over 3, that would become negative 80, plus 180 is 100. Okay, 60 times 1 over 12 is 5, plus 0 is 5. Okay, and then next, 60 times 1, 60 times 0 is 0, plus 0 would be 0. Okay, 60 times 0 plus 1 is 1. Okay, and then 60 times 7 over 12, that would be 35, because 60 and 12 would be cancelled. 12 would be cancelled, and then 60 becomes 5. Okay, so 5 times 7, the numerator is 35, plus 0 is 35. Now we check whether we still have negative numbers in the third row. Okay, since there is none, we're done. We don't need another wave of row operations. We're done. Okay, so by the way, guys, we don't need to write the slack variables here. Okay, if it is from a minimization problem, but in the maximization process, okay, we have to write the slack here, and then we have to write whatever variable. Okay, we have to substitute one variable here, okay, to our slack variable, and that would be the variable and the slack variable wherein that intersects, the pivot element. Okay, but we don't have to do it here in a minimization problem. Okay, so now it's time to interpret the results. Okay, so we have here, what we're looking for actually is B and M. Okay, how many chickens best, how many chicken meal. Okay, so your B here, okay, is equal to the number on the third row under B. So B is equal to 5, and then M would be equal to 0. Okay, and then our P here, okay, is not 1 but the number here, which is 35. And now we go back to our solution in the graphical method. Okay, this one. Okay, so using the graphical method, we arrived at this answer. We have to buy 5 chickens best, and we don't have to buy chicken meal, and it will cost us 35. Okay, so based on this, okay, actually this is going to be C. Okay, so our answers would be 5 chickens best, 0 chicken meal, and it will cost us 35. Okay, by the way, this P was originally C. Okay, this was derived from the minimization problem. Okay, so we're done. We arrived at the same answer. And that is how you do, or that is how you solve a minimization problem.